It is my pleasure to introduce someone who got me very excited about AI. Back in spring 2017, I'd taken a course at Carnegie Mellon University called Artificial Intelligence for Social Good, taught by Professor Fei Fang, who is a bright young professor at CMU, and she just finished her PhD under our next keynote speaker, Dr. Milind Tambe. Milind is the Gordon McKay Professor of Computer Science and the director of the Center for Research on Computation and Society at Harvard University. He concurrently spends time as a principal scientist and director of AI for Social Good research at Google DeepMind. During my PhD years at Cambridge, I also had the distinct pleasure of visiting Milind's group for 6 months out at Harvard. So without further ado, Milind Tambe.
Okay, well, thank you all for attending. Thank you for this kind invitation. And really a tough act to follow from the last speaker. So I'm going to talk to you about the work we've been doing in AI for social impact. So for the past 20 years, my team and I have been focused on advancing AI for social impact, focusing on topics of public health, conservation, and public safety and security, with the key challenge of how to optimize our limited intervention resources. And one big lesson we've learned is that social impact and AI innovation often go hand in hand. To give you a quick tour of some of our previous work, with respect to public health, we have large populations to serve, but limited number of public health resources. So a concrete example is work we have done with youth experiencing homelessness in Los Angeles. Harnessing the social networks of these youth, we are able to show that our influence maximization algorithms are far more effective in spreading HIV information and reducing HIV risk behaviors compared to traditional approaches. This work required innovation in the social network algorithms because those are not known in advance. With respect to conservation, we have large conservation areas to protect, limited number of ranger resources. So concrete example is work we have done in Uganda and Cambodia, where harnessing past poaching data, we are able to predict where poachers set traps or snares, and for the past several years have been able to remove thousands of these snares. In the past, following the attacks of 9/11 in the United States, we developed a new model called Stackelberg Security Games, developed new algorithms that were in use by security agencies in the United States, such as the Federal Air Marshals, the US Coast Guard, and others. If you were on a US air carrier, United, Delta, American, on an international flight, whether there was an air marshal or not on your flight, was our algorithm at work. But today I'm excited to share with you our recent work on using these so-called bandit algorithms for the world's 2 largest mobile maternal health programs. The first is Mitra, which is a Mumbai-based program where 200,000 mothers are registered at a time. Here I'll showcase the use of a technique called restless bandits. The second is a program called Kilkari, which is an all-India program where 10 million mothers are registered at a time. And here I'll showcase the use of a technique called collaborative bandits. And finally, I'll talk about these meta-level agents, how we can accelerate the process of AI for social impact. I wanted to give credit to the lead PhD student who did their work, so their pictures are shown in the top right-hand corner of the slide on which their work is shown. So let's begin first with the work with maternal health. The motivation here is the maternal health crisis we face today. The UN Sustainable Development Goal says that by year 2030, the maternal mortality ratio, that is mothers dying during childbirth, should be below 70 per 100,000 live births. Where we are today, in terms of the maternal mortality ratio, in the United States and Western Europe, the numbers are low compared to the UN target, but the worldwide numbers are more than double the UN target. I'm going to focus on India, where the numbers are rapidly declining, but still higher than the UN target. But I want to emphasize that this is a global problem. In states like Mississippi in the United States, for Black mothers, the maternal mortality ratio is 20 times worse than what it is in countries like Greece and Slovenia. So this is a global problem. We have been very fortunate in India to be working with a nonprofit called Arman, which is active in 20 states, work with 41 million mothers. And in consultation with Arman, the first problem we focused on is their Mitra mobile health program for new and expecting mothers. So this is a program where mothers register, and from the time they register to the baby being 1 year old, every week, the mother gets an automated audio health message. So the message is something like this: for you and your baby to be strong, you need lots of iron. It goes on. This is a small snippet of an audio message that's 2 minutes long. 141 such messages are delivered, and 3.6 million mothers have benefited from this program. So if mothers listen to these 141 messages, one a week, then they have shown through randomized control trials that the mothers and babies benefit significantly in terms of their health. 30% improvement in increase in infants with tripled birth weight at the end of the year, and so forth. So where do we come in? Unfortunately, 30 to 40% of the mothers who register become low listeners or drop out of the program. So how do we counter that? Arman has this call center from where they can give service calls to try to persuade these mothers to not drop out of the program. But the challenge is that there's 200,000 mothers registered at a time. Remember, weekly audio messages go to each mother each week. So all 200,000 mothers receive these audio health messages. But from the call center, they can only call 1,000 mothers live service calls. And the question is which 1,000 to call out of the 200,000 in order to maximize the total number of health messages that are listened to. To make this more concrete, consider a single health worker who has 5 mothers under her care. 4 shown in red have not listened to a health message. 1 shown in green has listened to a health message. She has a budget of 2 in this simple example. So supposing she calls the first 2 mothers in a live call, this turns out to be a good choice. These 2 who are in red turn to green. There's another one who was in red also turns to green. Now again, next week, with a budget of 2, who do we call? So supposing now she decides to call the 2 who are in red who have not listened. This turns out to be a bad choice because those who are in red remain in red, and those who are green also turn to red. They didn't listen. The point is that choosing 1,000 out of the 200,000 is not so easy, because a live call may not change a beneficiary state, and beneficiaries may change state on their own. So how do you choose the top 1,000 out of the 200,000? So we turn to a model called restless bandits. Now, for those who may not be familiar with this model, essentially we are modeling each mother as a Markov decision problem. So basically, a mother might be in a bad state. She has not listened to audio health message, or a good state. She has listened. We can take an action to intervene on the mother by giving a service call or not. And now there's transition matrices. This models the behaviors of the mothers. So if you give a service call, the probability of going from a bad state to a good state is 0.8. But if we don't give a service call, the probability of going from a bad state to good state is only 0.2. In reality, there's 200,000 of these mothers, so there's 200,000 of these Markov decision problems, and we have to pick the top 1,000. So this is done by using what's called a Whittle index. I'm going to skip over the technical definition, but what it is computing the benefit of intervening on this mother. So we can rank all of the 200,000 mothers based on their Whittle index, and this gives us what's the benefit of intervening on each, and then take the top 1,000 to call. There's an algorithm we had developed in 2016 to compute the Whittle index, so we can use that. Unfortunately, this algorithm requires us to know the behaviors of the mothers. If a new mother walks in, we need to know her transition probabilities. Fortunately, what we do have is that all the mothers who have gone through the program in the past, for them we have features: age, income, education, etc., and their engagement sequence. The mother was in a bad state, she got a service call, remained in a bad state, service call, good state, etc. So from that, we can learn a mapping from the features such as age, income, education to transition probability. So for example, if the age is 26, income 5,000, education 8th grade, probability of going from a bad state to good state is 0.3. So when a new mother walks in, we can predict the behaviors of this mother. The next step then is to optimize by picking the top 1,000 mothers using our Whittle index. We call this approach a 2-stage approach. First, we maximize learning accuracy, and then we optimize by maximizing decision quality. Now it's time to evaluate this program in the field. And so we did this with a study of 23,000 mothers in the field. They were divided into 3 groups. One was the restless bandit group, one was the round robin group, one was the current standard of care group. Remember, each beneficiary each week always got this automated health message. What changed is who got a service call. So we called 225 mothers per week for 7 weeks. That is, in the restless bandit terms, pulled 225 arms. In the restless bandit group, the 225 that we called were our algorithm determining the top vital indices. In the round robin group, we called the first 225, then the next 225, et cetera. In the current standard of care group, no one was called because that is the current standard of care. And now we want to know how many more messages were listened to in each group compared to the current standard of care. And what we find here, along the x-axis are different weeks, along the y-axis cumulatively how many more messages are listened to. We can see with the restless bandit group shown in blue, 600 more messages are listened to compared to the current standard of care. With the round robin group, there's hardly any improvement over the current standard of care. The point here is that it is important to optimize who to give service calls to. If we just call people at round robin fashion or random fashion, there's hardly any improvement over in their listening behaviors. And we can also show that the restless bandit group cuts by 32% the drop-off rate over the current standard of care. So this was a good result, satisfying result, but we could do better. And this is done by what we call decision-focused learning. So far, I've talked to you about a two-stage approach. First, we maximize learning accuracy, and then we optimize. And in many tasks you may be asked, let's maximize our learning accuracy because that will ultimately improve our performance. But in reality, what happens is that maximizing learning accuracy does not translate into maximizing decision quality. And so I can show this with a real-world example. So there's two data sets here from Arman. This orange data set, which has a higher predictive accuracy, so we can more accurately predict these mothers' behavior. The blue data set, which has a lower predictive accuracy, we cannot predict the mother's behaviors as accurately. So now if I say, let's do service calls based on these two data sets, you would say that the orange data set should lead to higher listening behaviors from these mothers. But in reality, the results are exactly the opposite. We get lower listening behaviors with the more accurate data set and higher listening behaviors with a less accurate data set. And why might this happen? So if you look at it from this is a simple example where on the x-axis is some feature like age, and you have mothers with different transition probabilities. Blue is low risk, red is high risk. And now if I tell you that I want to do a two-stage model whereby I first maximize learning accuracy, I learned this green regressor line, which is high learning accuracy. It predicts mothers' behaviors more accurately, but it misses all the red dots, the high-risk mothers. Instead, decision-focused learning changes the loss function to directly maximize decision quality. What it therefore learns is this other green regressor line, which gets to the high-risk mothers, even though it has a low learning accuracy. So we tested this decision-focused learning in the field with the study of 9,000 mothers, 3,000 in the decision-focused learning arm, 3,000 in the two-stage arm, and 3,000 with current standard of care. If you look at predictive accuracy, the two-stage model, we can see that it leads to higher predictive accuracy. But if you look at actual behaviors, listening behaviors, along the x-axis are different weeks, along the y-axis is cumulatively how many more messages are listened to. We can see that the decision-focused learning approach leads to much higher listening behavior. So this decision-focused learning with restless bandits is what we've deployed with Arman. The system is called Saheli. It means a friend in Hindi, but it's also an acronym. This is just to tell you that we worked very hard to come up with a good acronym. We've deployed it since April of 2022. It has served over 350,000 mothers. So it has prevented 30% of drop-offs as we can do tests. For bottom 25 percentile of mothers who listen very little, the content exposure has more than doubled. So more messages about iron and calcium and so forth being understood or being listened to. Does this actually translate into health behavior improvement? So we can actually show with a recent study with 21,000 mothers with matched intervention and control that the restless bandits not only lead to higher listenership, but they lead to better health behaviors. So for example, improved calcium, improved intake of calcium, iron, knowing more about the baby, such as the baby's weight. So significant improvements along all three dimensions. The point is that ultimately, this AI intervention is not only improving listening behaviors, but also improving actual health behaviors. I wanted to show you a small video from one of the beneficiaries who benefited from this program.
नव्हते ऐकत पहिला त्याच्यानंतर मला त्या ताईंचा कॉल आला त्या घरी आल्या मला समजवलं हा कॉल घ्यायला पाहिजे तुझ्या पोरांसाठी चांगला आहे हा मग तेव्हा मी कॉल घ्यायला लागले आणि ते कॉल ऐकून खूप बरं वाटतं की कोणीतरी घरचंच मला कोणीतरी समजवायला येतंय मग जसं ते कॉल ऐकते मी तसंच मी माझ्या पोरगीचं संगोपन करते.
So this is a mother in Mumbai, a city I grew up in. She's speaking Marathi, which is also my language. And therefore, it is deeply satisfying to see someone benefiting in Mumbai based on the research we have. There's also lots of underlying research that was motivated by this application. I'm not going to have time to go into that. But let me switch over to the more recent work we have, which is the Skillkari program, where this is a Government of India program. 10 million mothers are enrolled in this program at a time. And it's similar to Mitra, messages going out to mothers in their local language on the feature phone every week. It's managed by Arman. And again, we want to improve listenership. But there's a difference in how we are focused here. Rather than giving service calls, which are not possible at the scale of 10 million, here we are trying to identify what's the right time slot to actually call this mother to give that audio message in the first place. For example, for mother number one, 8 a.m. is not a good time, 12 noon is not a good time, 2 p.m. is a good time. These are mothers in rural India, they're out in the field, et cetera, so it's unclear when to call them. So the current approach is developed by Johns Hopkins, probably for a small-scale approach. It's called 9 times at random. It's called a retry algorithm, but there's no machine learning going on in order to improve the pickup rate. So we can't see pickup rates improving over time, and also there's a lot of waste of bandwidth. So our first approach was to use a stochastic bandit. So essentially what this is saying is we're going to treat each time slot is some kind of a bandit arm. So when we pull an arm, it's like try calling in that arm, and based on the success, if the mother picks up the call, that's a reward, that's success. So you can figure out which slots to call in. And there are standard algorithms that figure this out. But what we are trying to ultimately learn is this beneficiary pickup matrix. Mother number two, so along the x-axis, along the rows are the different mothers. The columns are different time slots. And we are trying to figure out the probability that the mother will pick up that phone in that time slot. For example, the probability mother number two will pick up in the 8 o'clock time slot is 0.92. Using these stochastic bandit algorithms to figure out this entire matrix is very difficult. We are learning about each mother separately. Too much exploration. If instead we can exploit the fact that these mothers have similarity to each other, then we can learn more quickly. We can collaborate across these different arms of the bandit, so to speak. And in fact, we can show that this matrix is low rank, that is to say the mothers do have similar behaviors, and we can develop algorithms that exploit this low rank matrix completion without access to real features. So we do not have access here to mother's age, income, et cetera. We have no information other than when do they pick up the phone. So there's an algorithm that does that. I'm going to skip over that. So first we ran a simulation study based on data from the state of Odisha. Along the x-axis are mothers with different pickup probabilities. Y-axis is how many retries before the mother picks up the phone. Higher is worse, lower is better. Blue is random calling, the current approach. Orange is the stochastic bandit without collaborating across mothers, so to speak. And green is our algorithm that exploits similarity amongst mothers. So this is in simulation showing that our algorithm works. What was exciting is we recently did a pilot test. So this is done in the state of Odisha in 2 districts, Kalahandi and Puri. And we had 2 groups of mothers, 6,000 beneficiaries, 6,400 mothers per group. And there's details of the study, but in a sense, after some training on one arm of 6,400, we tried our algorithm. On the other, they continued with the random calling. And the question is, was there any improvement in the pickup rate? And so this is a small-scale pilot study, just 2 weeks. And if we filter out people who always picked up or never picked up, then what we see here is a significant gain along different time slots of the day. So there are 7 time slots during the day. You can see that with 6 time slot 6, for example, there's more than 10% improvement. So this is showing that these algorithms can improve the pickup rates of these mothers. We are very excited now to continue these studies in different states in India, Andhra Pradesh and Assam. Ultimately, the goal would be a national deployment with 10 million mothers. So that's the ultimate objective that we have. So in the last few minutes, I wanted to talk to you about this idea of meta-level agents. So for the past 20 years, my life and that of my team has been that some nonprofit or government approaches us with some policy goals. For example, we have limited number of service call capabilities. How can we maximize performance across the population? And then we go through 3 phases. First, discuss a lot with the agency, what's exactly their problem, their constraints. Then, what's the right AI model? Is it a bandit? Is it a game? Is it a Markov decision problem, et cetera? And then we evaluate it in the field. And these steps consume a lot of human time. I mean, that's our time going into understanding the problems, really defining the model. But if you read our papers, none of that is mentioned. What is mentioned is the nonprofit came to us with a very, very specific problem definition, and magically we had a model that matches their problem definition. All of the effort that went into figuring out the exact requirements and the exact model is never mentioned. But that's where months and months of time goes. So the question is, can we accelerate it? And to that end, the recent advances in these large language models and so forth can be helpful. So we use these as meta-level agents. And so as a first step in this goal, the idea is that supposing we've already deployed something like the restless bandit model for our months. So they already have something that generates policies to maximize benefits across all beneficiaries. Now they want to change their policy goals. For example, we want to maximize performance, but slightly prioritize low-income mothers. Today, the way it would happen is that they would call me or my students. We would have to go change code and then generate new policies to satisfy their new requirements. The question is, we've now developed these decision language agents that can take these kinds of human inputs and then change the underlying code to directly generate these policies. So this works for simple commands. So something like prioritize low-income mothers. So you can take a large language model, it iterates through these different reward functions, and ultimately generates policies. We've tested on 16 different commands where the yellow here is a human being given the same command to change code. Green is the large language model, this decision language agent, changing code to generate policies. And if we test performance, we can see that yellow and green appear to be closing in on each other. So simple commands like prefer low-income mothers, prefer Hindi-speaking mothers, we can approach the performance of human developer developing policies by changing code. But when it becomes more complicated, when there are multiple objectives, low-income beneficiaries and older beneficiaries together, then there's some problems, and that's where some of the research is ongoing at this point. So I'll stop here. I wanted to express my thanks for listening in here. So we have focused, this is our most recent work, on world's 2 largest maternal mobile health programs. And I talked to you about restless bandits and collaborative bandits. These approaches are useful in many other public health challenges. For example, wherever there is health adherence needs for tuberculosis prevention, diabetes prevention, these models can be applied, and that's something that we have also been exploring. And secondly, we are now trying to see how we can accelerate the process of AI for social impact by using these large language models, these agents, in order to write code so that they can help us accelerate the whole process. So thank you for listening in.
Thank you for that excellent talk, Milind. I think we'll have time for one question. and then we'll have to keep to time. So yes.
It's so interesting. I was wondering if you also considering and also develop or have any challenge on developing the business model for the technology for social impact, especially how to make the intervention or the technology financially sustained to make the technology still accessible and then keep the impact, because I experience it's quite challenging to keep this technology for social impact, particularly to keep sustained financially after the grants or after the project, after the research. Thank you.
No, thank you. That's an excellent question. I mean, we face these problems repeatedly. I mean, you're exactly right. We can't ask a homeless shelter, which we've worked with, over 10 years to buy our software, or who's going to support that software, or for wildlife conservation agencies, exactly who can support that software. So I don't have a general solution in all of these cases. It's often been case by case. For example, with Arman, because of my affiliation with Google DeepMind, Google engineers help deploy the system, and they are the ones who can help in, when there are bugs that come up, they come and resolve those. But this is obviously not a general purpose solution. So I have some ideas that if we can have universities and companies and banks all come together and have a nonprofit kind of an exchange center where we may have nonprofits enter into this and say we have a problem, and then we can do matchmaking whereby university researchers or others can address this problem, and then it gets sustained because of tech companies and others who may want to donate to this project. Then this is a way in which we can have large-scale AI for social impact ongoing. But this requires a lot of entities to come together. And I'm talking to lots of people. Hopefully hopefully there'll be enough of us together to try to sustain it. But that's exactly the right thing that we need to do.
Thank you so much, Milind. I think that's in the spirit of CHIA as well, so we can help with that. Thank you.
Thank you.